Calculus, video 71, the second fundamental theorem of calculus. So this is sometimes called the second fundamental theorem of calculus, or sometimes just a part of the larger fundamental theorem of calculus. Right? So some textbooks separate these into two kind of different parts of the fundamental theorem of calculus, and some textbooks just kind of lump them together. Right, so I kind of like to think of this as the second fundamental theorem of calculus, or the second part of the fundamental theorem of calculus. In this case, either way, really, the goal here is the integral itself becomes a function by letting one of the bounds be a variable. Okay, so what does that look like? The integral itself becomes a function by letting one of the bounds be a variable. And so we have something like the integral from 3, which is constant, to, instead of a number up here for the upper bound, we'll have like a variable x of some sort of a function, let's say square root of t dt. Now I have to use t's here because I've already used x as the upper bound. All right, so in other words, where we've been doing these definite integrals with a constant as a lower bound and a constant as the upper bound, we now have one of the bounds being a variable, meaning it can vary among different numbers. The question is, what does that mean regarding the area under the curve? Remember that this definite integral gives us the area under the curve. What happens now when I let one of the bounds be a variable? So what does this mean for the area under the curve? The area under the curve. Well, let's start with a picture. So we have some sort of function here. In this case, my function, my f of t function. F of t is the square root of t. And so now this has become a t-axis there. And that function, square root of t, looks kind of like this. All right, this is f of t equals square root of t. Now, instead of having my area under the curve being from like 3 to 7, the area under the curve is from 3 to some number x. And because x can change, right, the area can also change. If x is 4, then it's a smaller area, and if x is 5, it's larger, and if x is 6, it's larger, and if x is 7, it's larger. One way to that I think helps think about this is really thinking about this as a time axis, right? And so like over time. So I picture this, okay, what happens when x is 4 seconds? What happens when x is 5 seconds? What happens when x is 6 seconds? And what's happening is x goes from 4 to 5 to 6, right? As x goes from 4 to 5 to 6, the area under the curve, in this case, would get larger, right? The area under the curve is going to change as, in this case, as x grows. But in general, the area under the curve is going to change as x changes, as that upper bound changes. Okay, so by letting one of the bounds, in this case the upper bound, be a variable, we're getting a change in the area under the curve. What we want to find out is what is the rate at which the area changes. That's our big question. What is the rate at which the area changes? Okay, so if you're thinking about this, if x is 4, maybe the area is like 6.5. And if x is 5, maybe now the area is 8. And if x is 6, now maybe the area is 10, right? The area is changing. If you picked a particular value of x, we would want to find out the rate at which the area is changing. Okay, so big question, calculus, physics, engineering. What operation gives us a rate of change? Right? A rate of change is given by a derivative. Right? That's an important question not just in this context, but in lots of other contexts. If we want to know the rate at which something changes, we find its derivative. So the derivative gives us the rate of change. Okay, so if I want to answer this question, what is the rate at which the area is changing? I have this. The answer to that question is this. It is the derivative with respect to x, of the integral from 3 to x of square root of t dt. It's the derivative of that area as the area changes. That gives us the rate of change. Right? The part inside the parentheses there, that is the area for particular values of x. As x changes, the area changes. The derivative of that gives us the rate of change. Okay, there are two ways to do this, to solve this. There's the long way, and then there's the shortcut. The shortcut is what we call the second fundamental theorem of calculus. We're still going to use the fundamental theorem of calculus, which is that the integral is f of b minus f of a, but this second fundamental theorem, or the second part of the fundamental theorem of calculus, allows us to find this derivative in a shortcut manner. But we're first going to do it the long way to show that it works with the shortcut way. Okay, so first way, the long way. 1. The long way. The long way is this. We will simply do the integration, and then when we get an answer for that, we will take the derivative of it. So we'll have the derivative of the integral from 3 to x square root of t. Instead of square root of t, let's say t to the 1/2. That makes an easier integral, dt. We'll work our way inside out, so we'll do the integral there. And we'll have the derivative of t to the 1/2, that would be t to the 3/2 if I add 1, divided by 3/2, that would be 2/3, evaluated from 3 to x. Okay, that would be the derivative of 2/3 times, plugging in x first, I get x to the 3/2, minus, now plugging in 3, I get 3 to the 3/2. Or, I mean, you could use a calculator and figure out what exactly that is. 3 to the 3/2 is some decimal. Well, let's go ahead and find out what that decimal is. 3 to the 3/2, I've got about 5.20. So about 5.20. So we get the derivative of, let's write this as 2/3 x to the 3/2, and go ahead and distribute that 2/3 to both of these. 3 to the 3/2 is 5.20, 5.196 times 2/3. I'm getting 3.46 approximately, so minus 3.46, distributing the 2/3 to the 3 to the 3/2. Okay. All right, so that would be the area under the curve. Right, what's in parentheses here is the area under the curve. This part right here in parentheses tells us the area under the curve. And what it does is it tells us the area under the curve for whatever value of x you want to give me. If you tell me that x is 4, then this will tell me this is the area under the curve from 3 to 4. And we would just plug in 4 into the x, and that would tell me what the area of the curve is from 3 to 4. If x is 5, it would tell me the area under the curve from 3 to 5. Right, so this is a function that tells me the area under the curve for any value of x. Okay, so not just 4, but any value of x. The derivative of that is the rate at which that area changes. So if I want to find the rate at which that area changes at a particular value of x, we'll take the derivative. The derivative of 2/3 x to the 3/2 minus 3.46. What is the derivative of 2/3 x to the 3/2? Well, that would be 2/3 times, bring the 3/2 down, x to the subtract 1 from 3/2 is 1/2, and the derivative of 3.46 is 0, And let's see, I get the 3's cancel and the 2's cancel, and I get x to the 1/2, or square root of x. And this is the rate at which the area changes. In other words, if we let x equal 4, right, what was in parentheses up here gave us the area from 3 to 4 if I just plugged in 4 into that x. What is down here, the square root of x part, is the rate at which the area changes if x is 4. So if x is 4, square root of 4 is 2, it is saying that the area is changing at a rate of 2, if you had some units there, you might say 2 centimeters squared per second, or 2 meters squared per second, something like that, right? But that is the rate at which the area changes. Okay, that's the long way. The second fundamental theorem of calculus says there's a shorter way. Go back and see if we can find or think about the shorter way here. We started with this. We started with the derivative of the integral from 3 to x of t to the 1/2 dt, or if you wanted to, square root of t dt. And we got an answer of square root of x. What's the shortcut here? The shortcut is we can simply take this x, this upper bound x, and plug it in to the t and get our answer. And the reason this is because what you're doing are basically inverse operations here. We're doing the integration, and then we're doing the derivative of that. So if you integrate something, and then you take the derivative of it, you wind up basically with what you start with. So therefore, we can just take the x, plug it in, shortcut. The second fundamental theorem of calculus, I'll just abbreviate fundamental theorem of calculus with FTC. The second FTC says this. The derivative of the integral from 3 to x of square root of t dt, instead of integrating and then taking the derivative, all I have to do is say this is equal to the square root of x. And I'm done by the second fundamental theorem of calculus. That's it. That's all we have to do. If we want to write this out in kind of more of a general form, the second fundamental theorem of calculus says this. The derivative of the integral from some constant a to x. I'm going to pause there. Notice it didn't really matter what constant a I started with, because go back up to the top in the long way. The constant 3 here gave us, when we plugged it in, the value of negative 3.46. But when I took the derivative, what happened to the negative 3.46? It went to 0. So it didn't really matter whether I started at 1 or 3 or 7, right? Because when I do the derivative of that constant, it's going to go to 0. So any constant here works. Of some function in terms of, it doesn't have to be t, but it can't be x, because we've already used x, dt, is equal to, basically we're going to take the x, we're going to plug it in for all the t's, and that becomes whatever that function f of t is, but now in terms of x's instead of t's. There you go, the second fundamental theorem of calculus. At least kind of. There's actually one more nuance to it. The nuance is, what if the variable, the upper bound variable, wasn't just an x? What if it is itself an entire function? What if instead of going from a to x, we went from a to x squared, or from a to x cubed, or from a to the sine of x, or a to the square root of x, but some function of x and not just x itself? Okay, well let's try that once again the long way. Maybe we'll switch functions here. What is the derivative of the integral from 1 to, let's pick a more complicated function, not too complicated, how about just x squared, of 4 minus 3t squared dt. Okay, long way. The long way, we will do the integration. we will do the derivative of the antiderivative of 4, we have 4t, 3t squared, we'll integrate that, we'll get minus t cubed, and we'll evaluate that from 1 to x squared. So we'll have the derivative of, plugging in the x squared, I get 4x squared minus x squared cubed, and then minus 4 times 1 minus 1 cubed. That would be the derivative of 4x squared minus x to the 6th. Let's see over here. 4 minus 1 is 3, so minus 3. Now when I do the derivative, we get 8x minus 6x to the 5th plus 0, and that is the rate of change of the area. Okay, but we don't want to do it the long way. We want to use the second fundamental theorem of calculus. We want to use the shortcut. But we kind of run into a problem here, right? If using the second fundamental theorem of calculus, or some books have just the fundamental theorem of calculus, if we look at the derivative of the integral from 1 to x squared of 4 minus 3t squared, 4 minus 3t squared dt. Earlier we said all you have to do is take that x squared and plug it in, right? We said just take the x squared and plug it in for the t and you'll get the right answer. But what happens when we do that? We get 4 minus 3 times x squared squared, right? And that would be 4 minus 3 times x to the 4th. But that is not this. And a shortcut should match the long way. Otherwise, we didn't do it right. Well, the key here is when you're doing the integration, you end up plugging in x squared, and then you take the derivative. That x squared is acting like the inside part, right? It's like the inside of the thing that I'm plugging it in. You're plugging x squared into the f of t function. Right. When you do the derivative of something, you take the derivative and then you multiply it by the derivative of the inside and you have a chain rule. That's kind of what's going on behind the scenes here. When we have something besides just x, we have some sort of function of x, like x squared in this case, we can just plug in the x squared like we did now, right, with the x squared right here. We can just plug it in, but we then have to take the entire answer here and multiply it by the derivative of x squared. That's like u prime, multiplying it by u prime. So the derivative of x squared is 2x. And then we multiply that through and we get 8x minus 6x to the 5th, which is exactly what we have up here. So, as a recap, if your function, if your upper bound here is a function of x and not just x itself, you have to then multiply it by, you plug in the x squared, but then you multiply it by the derivative of that upper bound. Okay, it looks something like this. The more general form of the second fundamental theorem of calculus says if you have the derivative with respect to x of the integral of a to some function of x, let's call that g of x, of f of t dt. That is equal to, you're going to plug the g of x into the values of t here. So that's going to be equal to f of g of t, right? Not just plug, sorry, f of g of x, my fault. F of g of x, right? You're not just plugging the x in for the t, you're plugging the entire g of x in for the t. In our case up there is like the entire x squared goes in for all the t's. And then we multiply that by g prime of x. That's the more general form of the second fundamental theorem of calculus.